at the end of the last class, we worked out the consequence of word identities for currents that were whose holomorphic part was entirely whose current such that Jz was purely holomorphic and Jz bar was purely anti-holomorphic. We found that the word identities for these terms could be expressed in terms of an operator product expansion between by a statement about the operator product expansion between this current and operators that transform under the symmetry generated due to this current. Now, many of you don't know what the operator product expansion is, and there's an interesting manipulation involving commutation relations of these currents that we want to discuss in today's class, among many other things. So, in order to set the stage for that, I'm briefly going to review this thing called radial quantization, which is a question that came up in the last class also. The question that came up in the last class was that we were interested, before starting our fancy study of conformal field theory, studying a string moving in a cylinder, space and time. However, in the last class we looked at the Euclidean theory on R2, and somebody asked, why is that? And I said the reason is that in a conformal field theory can go from one to the other by conformal mapping. We're going to look at look at that in a little more detail, just to start the class. Okay, so in the first 3 lectures of the course, we did a Lorentzian expansion of the oscillators of the space-time coordinates of the string, and our expansion was, and I will have to help you here, what was it? Sum was alpha, so x was x naught plus alpha prime p tau, that's right, plus sum over n was an I alpha n alpha minus n is a e to the power, how did it go? Let's see. So the creation operators have to have positive frequency. So we have e to the power, these alpha, let me call this alpha n. Alpha n e to the power minus I n tau plus sigma, let's say. By n. Well, somebody disagrees with this. Maybe I got the plus sigma minus sigma. That's what is alpha? What is alpha bar? The only relevant thing is that's it. This guy is minus when this is plus. That's a physics. Okay. Plus similarly alpha n I alpha bar n n equals I n tau. Okay, we have this Lorentzian expansion. I might at some point just to match Kolchinski's conventions, I might flip this I to minus I. Those are completely. You have to put either an I or an minus I, so as to get alpha n be the complex conjugate of alpha minus I. When you put I or minus I, it was entirely up to your mood. Okay. So fine. So we have this kind of expansion. Now I'm going to take this expansion and continue into Euclidean space. So what's the continuation? You remember we discussed that in quantum mechanics. If you have x dot squared minus a b of x dt, e to the power I times this, the continuation t Lorentzian is equal to minus I and t Euclidean was the continuation that gave us the Euclidean function. Okay, so this tau here is tau Lorentzian. What we have to do is to replace it by minus I tau Euclidean. Okay, so we make the replacement. Tau goes to minus I tau Euclidean. Tau goes to minus I tau Euclidean, and I think I want to, okay, let's first make a replacement. So then we have x is equal to x naught plus alpha prime p minus I tau Euclidean. Okay, plus sum over n. Maybe, yeah, okay. Plus sum over n I alpha n by n e to the power minus I n minus I tau Euclidean plus sigma plus the opposite guy, right? Plus sum over n I alpha bar n by n e to the power I n minus I tau Euclidean minus. Okay. Now we're going to do some renaming. We will call this sigma 1. I believe. Just let me check that I'm not getting sigma 1 and sigma 2 opposite dimensions. Yeah, no, he has the same sigma 1. So sigma goes to sigma 1 and tau Euclidean is equal to sigma 2. Changing things. Okay. So if we do this, what does our expansion become? So we get that x is equal to x naught plus alpha prime minus I alpha prime p tau Euclidean, which was sigma 2. Okay. Plus sum over n I alpha n by n e to the power. And now what does this become? This becomes e to the power minus I n sigma 1 minus I sigma 2. Okay? So if we write W is equal to this, W is equal to sigma 1 plus I sigma 2. So clearly W bar is equal to sigma 1 minus I sigma 2. So this guy becomes e to the power minus I n W bar. Okay. So maybe we want to flip what we call bar. Okay. So this guy will become. Okay. And then we'll have I alpha n by n minus I n. That's clear. Okay. This guy is a bit irritating because it's written in terms of I sigma 2. What? Plus I n boom. W no. Well, the W bar differ only by the sign of. Oh yeah, you're right. Plus I.
Minus I inside there, right? There was minus I there, which continued to be minus I downstairs as well. And so you take out the minus, it will become.
Yeah. Plus I n. You're right. It's plus I n. Okay, now we'll write the sigma 2 also in terms of W as sigma. Okay, so I sigma 2 is W minus W. So minus I sigma 2 is W bar minus W by 2. So x is equal to x naught, which is just by itself. And then there's the completely analytic part of it, which is minus alpha prime p w by 2 plus sum over n I alpha n by n by n w plus alpha prime by 2 P W bar, sum over plus sum over n, I n, this was alpha n bar by n is bar minus I n. Okay?
How do you get this?
Which n here? The n was, it just,
No, upstairs. I in alpha.
where, sorry.
It's just like that. It's just alpha.
Thank you. Okay? So this was our expansion for the harmonic oscillator with this, where we just move to Euclidean space on the cylinder, on circle edge time. What is this W space? This W space is clearly a cylinder because the real part of W is periodic with periodicity 2 pi, because sigma was bigger. Sorry. The imaginary part of W is periodic with periodicity. Sorry, sigma 1. Sigma 1 was periodic with periodicity 2 pi, and sigma 2 was just went from minus infinity to infinity. So the space that we're covering is a cylinder where the coordinate round here is the real part of W, coordinate up there is the imaginary part of W. There's some complex structure that we've adopted. Okay, great. Now, consider the following analytic transformation. Z is equal to e to the power minus I. Okay? Consider the following analytic transformation. Z is equal to e to the power minus I. Under this analytic transformation, how does this field look? But before transforming the field, let's just look at the geometry of this transformation. Suppose I have two planes here. The first is the W plane. Okay? So, in the W plane, the real part of W is periodic with period 2 pi. So I'm going to draw all of it. Just draw it from minus pi to pi. The imaginary part goes all the way. So this is effectively the relevant part of the W. Okay. Now I draw the Z plane. Z, as you can see in a moment, just goes over the whole plane. Okay. So what is this map here? The first thing that we'll do is look at modulus. So look at modulus of Z is equal to e to the power minus I. Now, anything that's a phase goes away in the modulus, so the real part of W goes away, into I sigma 2. Okay? So that's equal to e to the power sigma. So, any point here, maps to some place here, such that the modulus of Z is determined by where you are in sigma 2. If you go way down, the modulus of Z is very small. If you go way up, the modulus of Z is very big. Next, let's look at the argument. Clearly, the argument of Z is just up to a minus sign, sigma 1. Okay? So, where you are on the circle of the cylinder tells you what angle you are in the Z plane. Okay? So, if you take a little cylinder piece, a bit of the cylinder here, that maps to a circle here. You take a little bit of the cylinder here, that maps to a circle there. Is this clear? So we sliced up the Z, the map from W to Z gives you a slicing of the Z such that lines of constant time in W map to circles, concentric circles around the origin in the Z. Is this clear? Okay? And the argument in the Z plane is simply which angle you were in or which position you were in on the cylinder and the W. Now, this is going to be very important because if we are interested in actually, that's economical quantization of our theory, we were doing the Lorentzian theory, which we did correctly in the first 3 classes. So, the Euclidean continuation of that is just a cylinder. But as I explained, because of this conformal transformation between the cylinder and the plane, you get any calculation that you're interested in doing on the cylinder, you can equally well do on the plane. Okay? But it's important to note that lines of constant time, if you're worrying about the actual physical Lorentzian problem on the cylinder, lines of constant time are actually circles, lines of constant radius. Okay? Lines of constant radius, okay, in the Z plane. Okay? So for instance, suppose you wanted to write down, you had a current, and you wanted to write down the charge operator corresponding to that current. What do we normally do? We take the charge operator, dot it with the surface we're integrating over, and choose that surface to be a surface of constant time. Where will we choose that surface of constant time? On the physical place where we want to actually quantize it, the W. And then we have to take that and map it to whatever it maps to on the Z plane, which happens to be concentric circles around the cylinder. So a charge, for instance, a charge operator can be written as a contour integral on lines of constant radius. Is this clear? This is what the standard thing that you would do to represent the charge at a given time on the W. Okay. Moreover, have we seen this charge operator before? We have. We saw this charge operator because if you remember, we were studying this word identity, which had del mu and K mu, with insertions of other things. And then we used that Gauss law, Stokes law or something like that to convert this into a surface integral. Okay? The surface integral was the surface integral of the operator of J dotted, normal to the surface. That's exactly what we should do when we measure a charge. So if we were not specifying about which surface we chose there, but if we happen to choose that surface to be the surface of constant radius, that would be the standard contour to choose to evaluate a charge on the cylinder. Now, we were not terribly careful about where we chose the contour, just because it doesn't matter very much unless you pass another operator, because charge is conserved. We see that in more detail. But conceptually, you can think of this as being evaluated on one of these radial surfaces, and then you allow all the manipulations that don't care that if you can change the contour without changing the answer. Okay?
Sorry, does it look somewhat like time ordering? Because if I have some operator in the cylinder below at earlier time, that will be like an operator enclosed within the contour, and so it's like the operators only enclosed within the contour contribute correspond to.
Your intuition is absolutely right, and then we'll be talking about that in the next 5 or 10 minutes.
Also, in light-mode reach quantization, there was no relevant symmetry, so the conformal transformation is equal to
No, there was relevant symmetry. There was the symmetry of conformal transformations. And then we chose to fix that. Okay? But right now what we are doing is just studying the free scalar theory for itself. Okay? We'll worry about in 2 or 3 lectures, let's say, we'll worry about how to use what we've studied to go back to understanding a better quantization of the story. Okay? So I would ask you to hold off on that for a few lectures. Right now just take the conformal field theory defined by the action del alpha x, and let's study its physics. Clearly that will be relevant to us. Okay? So hold off to questions about how it's going to relate once again to quantization of stupidity. We'll address that in great detail. But hang on for that. Okay. Great. So now, once we've got this understanding, I want to go back to what we derived last time about the operator, about the singularities. About the singularity. Oh, maybe bit before that, let me explain to you now, since I can do it, let me explain the state operator. Just so that I can explain the operator product expansion to you. Okay. So, the existence of this conformal field here tells us that the existence of this conformal transformation tells us that in any two-dimensional conformal field here, and in fact everything I say is valid for every dimension. We're studying 2, but it's the generalization to every dimension study is immediate. Okay? That in any two-dimensional conformal field theory, there is a deep map between states and operators. Okay? The map is between states of the theory quantized on the cylinder and operators of the theory. When I tell you about operators of the theory, operators are just insertions inside a path integral. I don't have to tell you where the path integral is. It's a local property of the path. Okay? So there's a deep map between states of the theory on the cylinder and operators of the theory anywhere, for instance, in R. Okay? What is that map? So in order to try to understand this map, let's first do the following. Suppose I was in R2 and I had an operator insertion. Okay? There were other operator insertions outside the unit disk, but no other insertions within the unit disk. Suppose I was in this situation. I'm interested in computing the correlation function of this operator inserted here with arbitrary other insertions outside the unit disk. Well, this correlation function is a path integral. So what I have to do is to do the integral over all the fields outside, inside, and on the unit disk. So if I want to, I can divide up this path integral into fields inside the disk, a path integral into fields outside the disk, and a path integral on fields of fields on the disk. Okay? So let me call the fields on the disk x of sigma. It's a function only of sigma 1 because sigma 2 on the disk is just 1. Okay, it's just the way it's maybe now that we're in Z plane, let's call it theta. It's just a function of theta. Angle mod z is just 1. Okay? It's an insertion on the disk. No, there's no insertion. Just name for the fields on the disk. Okay? So what we would have had is a path integral with dx of z. This is for mod z less than 1. dx of theta. This is for mod z equals 1. And dx of z for mod z greater than 1. Okay, what we've got now is that the path integral over the stuff here is complicated because of all the other operator insertions outside the disk. Because we've got only one operator inside the disk. So we could just once and for all do this path integral for all of the fields with mod z less than 1. Doing that path integral gives us what? It gives us some function of what the values of the fields are on the unit disk. It cares about what the values of the fields are on the unit disk. It doesn't care about what they are away. Because the path integral, the field theory that we're studying, is a local field theory with at most one derivative in it. Okay? So when we're doing the path integral of integrating on points here, no, it cares about what's here, but it doesn't care about what's here. Is this clear? Okay? So this is psi of x of theta. That's this path integral, and of course it cares about which operator. We've inserted some operator here. It cares about which operator we insert. Okay? Then we have to do the integral d of x of theta, and then the integral over this is mod z 1, and d of x of z for mod z greater than 1 for all the other points, and we've got all the other insertions O1, O2.
So what's
X of theta? Because the action here has at most one derivative in coordinates. So imagine doing the integral, discretize this integral. So, you've got points here, points here, points here, points here. When we do the integral over those fields, it only cares about the answer only cares about the fields that appear in the action involving these fields. One derivative is this minus this divided by epsilon. So it cares about what's here. So it doesn't care about what's here. Because those don't count. Is that clear? Yeah.
Does this psi of theta, does it depend on the
Psi of x of theta.
psi of x of theta? Does it depend on the this radius of this unit?
Well, I've chosen the unit disk. If we had a different radius, it would depend. It would depend, though in a very simple way. Because I was going to say this, but let me just say it now since you brought it up. You see, transformation of radius in Z is can be achieved by transformation of time in W. So it depends by Hamiltonian evolution. If we choose the Hamiltonian as the Hamiltonian in W. So it's very simple dependence. We'll come to that. But otherwise I've chosen unit rays.
in principle, all fields live everywhere. So the decomposition of the measure.
What do you mean all fields live everywhere?
I mean all bosonic fields x mu live over all the complex planes. So
but the path integral is an integral over x at each point. Imagine a lattice regulation over there. Okay? What do you mean by path integral of x of mu? It means path integral of x at each lattice point. Okay? So since I'm doing an integral, I can choose to do the integral of some values before this. Now, if you're a mathematician, you might worry about whether you can compute and all that. But we'll regulate, everything will be okay. Okay? So it's just an integral. I can choose to do one integral before the other, full stop. Is this clear? Okay. Now, look. What do we have here? This psi of x of theta is some functional of the fields. Psi of x of theta is some functional of the fields at a given radius. If we went back to the W plane, what would this be? We had a cylinder in W. We've got some functional at some particular time 0, and then insertions like this. Now, what we're doing is a path integral over all of the cylinder in the W plane, but weighted with this functional at t equals 0. There's a name for doing such a path integral. If you had a functional here and another functional up there, do you know what this path integral represents in Hilbert space? Suppose I have only one function here. Suppose I ended the cylinder somewhere else with another function. Instead of psi, I call it chi. And then I put insertions all over. What is that the path integral representation of? A transition amplitude between the state psi and the state chi. Okay? This is a general fact about path integrals. That cutting the path integral over constant time, okay? Cutting the path integral over constant time gives you states in the Hilbert space way of looking at things. Is this point clear to everyone? If there's anyone for whom this is not clear, okay, let me say a little more, and then if this is not clear, you should ask questions. It's very important. Okay? Let me remind you of a baby version of this. Suppose you're doing non-relativistic quantum mechanics, and you wanted to compute chi e to the power minus I, so no operator insertions, times psi. Well, what do you do? One way of doing it is to do chi y integral dy, insert e to the power minus I x psi. Then this thing is the standard path integral from x to y. But that answer is convoluted, is multiplied by the wave function of the final state and the wave function of the initial state. And then you also do the integral over y and x. So if you do a path integral from one time to another, convoluting, so the path integral from one time to another is a functional of the fields at this time and the fields of that. If you choose to convolute that functional with something like this, that thing is just the state that you're computing the path integral with as starting with, or the state that you're computing the path integral as ending. Okay? So general fact about path integrals is that if you do a path integral from one time to another, the answer depends, is a function of the fields you start with and the fields you end with. Instead of looking at that functional, if you choose to take the function and convolute that functional with a function of the starting values and a function of the ending values, what you're doing is computing a transition amplitude between the initial and the starting final state, and the wave function of the state that you're convoluting, that you're starting with, is this in Schrodinger representation, as you can see from here. Right? Here, this thing would just be in Schrodinger representation, what we would call it phi of x. Okay? Is this clear to everyone? So path integrals done from one time to another, convoluted with functionals of the boundary values at the first time and second time, represent path integrals that are transition amplitudes between one state and another, and the wave function of the state. The wave function of the state is simply the function with which you convolute. In this case, psi of x. Is this clear?
But here there is just a convolution with the initial time.
Yes. It's just convolution of the initial time. Doesn't matter. So we're going to start here and go up to infinity. So that will be effectively the Euclidean space projecting onto ending with the vacuum. Yeah. But it doesn't matter. The important point here is that manipulations in this space lead you to a formula for computing correlation functions that involves a function which is a state in the Hilbert space of the theory. Okay? So there are two ways of computing this correlation. A, compute the correlation by doing the path integral over all fields. B, do the correlation function, compute the path integral only over fields at and above the unit disk. Convoluting the path integral, but this sounds indefined. Because if we do the path integral with the unit disk cut off, then the answer depends on the value of the field at the edge of the unit disk. And then you take that path integral, convolute it with this particular state. That gives you a well-defined correlation function. Is this clear? There are two different ways of computing this same correlation function. A, computing the correlation. B, doing the path integral only over fields that lie to the exterior of the unit disk, plus fields that lie on the unit disk convoluted within the particular wave function.
But does the state into account any operator insertions that are happening inside?
No. So far we've assumed that there is only one operator inserted inside the disk. We don't. Anyone unclear about this? Vishal, you're not looking happy. Are you happy? Okay. Okay. So, this way is a way you can go from operators to states. Given an operator, I can define a corresponding state. What good is that state? That state allows you to compute correlation functions involving insertion of that operator. Almost as well as knowing the operator, the almost becomes pure. Now, there's unhappiness because this can only work if we've got. You see, I've talked about the origin, by the way, but R2 is a translational invariant space. So I can choose any point and make that the origin. Okay, so if I've got an operator inside, I'll choose that as the origin of my R2. See, only lack of generality here. The only lack of generality in what I said is that I assumed that there are no other operators inserted up to unit distances away from this operator. But suppose there was another operator inserted. Suppose there was another operator inserted, let's say mod z equals half. Then I could play the same game by choosing a smaller disk, as in your question. Hang on, let me finish it. Okay. Then I could play the same game with a smaller disk. That of course would be a different state because I'm doing a different path. Okay, this is the path integrator with this disk and the insertion. That gives me a different state. What is the connection between this state and that's the state with the unit disk and the state with the smaller disk? The connection is very easily seen if we transform back to the W cylinder. Transforming back to the W cylinder, what is the difference between this path integral and this path integral? It's simply the evolution operator from this time to this time. Because that's what a path integral with no insertions is. It computes the evolution. Evolution happens according to the Hamiltonian. So, the relationship between one state and the other is the action of e to the power IHT e to the power minus IHT on the states in Lorentzian space or the appropriate Euclidean continuation. So e to the power minus HT on the states. Okay? So, although you would get different states here, and if you did the integral over the unit disk, if you knew the Hamiltonian of your theory, you knew how to translate states back and forward in time, you could predict what state you would get in the smaller disk, knowing what state you got in the bigger disk. In particular, we will find it convenient in every manipulation we do to use as a basis of states that are eigenstates of the Hamiltonian. In which case, the evolution is very simple. It's just by phase in the Lorentzian space, or a magnitude in the Euclidean space, and you know the phase or the magnitude if you know the energy. Okay? So, suppose, where are we going? I wanted to say that if I knew the state on the unit disk, and I know a little bit more about the theory, okay, I know that gives me an alternate way to compute all correlation functions in the theory. Even if there are things inserted quite near. Because there's nothing else inserted at that point. Okay? You take that state, shrink it to the amount you need by time evolution, and then do the path integral with that state. You may think that this is a pretty pointless, this is hardly simplifying your life. But as in many of these kind of manipulations, the point will not be that you will actually compute correlation functions like this. It is that this way of thinking will lead you to understand structural properties of correlation functions. That would be very hard to understand, of course. Okay? Great. So we discover a map between operators and states. And the key point of that map, the defining property of that map, is that the state contains all the information that you need to compute correlation functions of that operator and any others by the procedure we enunciated. Yes?
The way I can see it at this stage, the way we have done it, is that for each operator you have shown there exists a state.
Yeah.
But how can you still be sure that there are no states in the Hilbert space for which there
How do you know? What about the other way around? That's your question?
Yes.
Coming. We've shown one way, we've shown the other. Hang on. You had a question. Sure. Okay, excellent. Great. Now, there's an excellent question here. The question is, look, you've made a big song and dance about going from operators to states. Okay? But surprising that you can go from operators to states? Because just in quantum mechanics, if you take an operator and you act on a distinguished state, for instance the vacuum, you will get a state. That generates a map from operators to states. That's not surprising because there are more operators than states. Operators in quantum mechanics are matrices. States are columns. So it's easy to go make a map from bigger space to a smaller space, but stuff is the other way. How do you? So you've got a map from operators to states, but this is not much of correspondence unless you also have a map from states to operators. And the intuition I gave you suggests it's impossible because how do you make a map from operators to matrices? Sounds crazy, eh? Nonetheless, in conformal field theory, there is such a map. And it's not crazy because we're not looking at all operators in theory, we're only looking at local operators. Instead of local operators, we're all matrices on Hilbert spaces, some special things. And one wonderful thing about conformal field theories is that there is this one-to-one map. Okay?
This side of the map is true for any field.
This side of the map is true for any field. That's correct. That's correct. Now, what I want to do is establish a map from states to operators. Okay. What is the map from states to operators? Well, in order to get that map, once we understood the, by the way, once we've understood the map in this language, okay, people talk about this map in Hilbert space language. It's far more convenient to think entirely in terms of path integrals. Think about this. Okay, the way I talked about this map, actually in Hilbert space language, this is the same thing as acting this operator on the vacuum. Okay. But I've not talked about it that way. We'll come to it at some point. This one, it's just completely operational. Right? If you want to compute a correlation function, this map gives you a way to compute the correlation. Now what we want to do is to reverse that operations relationship. Okay? If I've got a wave function, how do I construct an operator? Suppose you give me a wave function in the Hilbert space theory. Okay? How can I construct an operator such that the insertion of that operator would lead to my state by the forward procedure we just enunciated? But it's very, very simple. In fact, we've already seen it. You see, because the state, let's say it's become state living form. But as we said, because shrinking in radius in a conformal field theory is just a unitary operation. Okay? Coming from Hamiltonian evolution on the cylinder. Okay? Knowing the state is the same as knowing the same state. They're all supposed to be concentric circles. Okay. Knowing the state is supposed to be it's the same as knowing the state for any value of radius. So now, let me consider the state an infinitesimal radius. Okay? If I insert this state at infinitesimal radius, okay, this is just an insertion into the path integral that depends on the values of fields only infinitesimally near to the origin. Any insertion into the path integral, any insertion by a function of fields infinitesimally near to a point is a local operator insertion. That's what a local operator insertion is. Right? With some function of x of that point. And then you can allow derivatives. Okay. So, if I was looking at within the path integral, so I shrink this down to, you'll take the limit that goes down to 0 size. Now what am I doing? I'm doing the integral of b of x of sigma over all x, including x of 0, but the integral at x of 0 is weighted by a function, which is what you got by taking the wave function and translating it, shrinking it down to 0 size, translating it down to t equals minus infinity in the W. Is this clear?
Yeah, what was the question on this? Operators radius are related by some transformation. But I don't know that is the Hamiltonian. That is true for any field theory.
That's true for any field. No, it's not true for any field theory because the Hamiltonian depended on the fact that radius is the same as time evolution on the cylinder. That came from conformal transformation. Radial evolution in general in the field theory is not generated by some Hermitian operator. But in a conformal field theory it is. Okay? So, in a general field theory, you might lose a lot of information in going from here to here. Okay? But in a conformal field theory, you don't. It's just Hamiltonian evolution. Unitary evolution of a state. Okay? So,
the fact that radial evolution is Hermitian is because of the scale invariance, right?
because scale invariance.
So, will this work for any scale invariance here?
We needed the conformal transformation to go from the cylinder to the plane.
So, any scale invariance here in R2 will have a Hermitian radial.
Will have a Hermitian radial generator. It probably is if you think about it. Yeah, so if there is nice dilatation operator, that's probably true. Of course, it's believed that apart from free theories, every scale invariant theory is also conformally invariant. So it's a bit hard to make that question contentful unless you had a non-trivial theory that was scale invariant without it. Yeah, but you're probably right that if there was such a theory, you could probably make sense of it. Yeah, that's a good point. Okay? So now what we've got is a map the other way around. Given a state, I have shown you how to define an operator.
I did not understand how we got the operator.
How did you get the operator? So what is an operator? Let's remember what an operator is inside a path integral. Okay? So we've got a path integral is dx and f some form. Weight this path integral, according to Parkinson says, you weight this path integral by some function of x of sigma. It can only depend on x of sigma and points in its neighborhood. So you allow derivatives. Okay? This object, such an insertion is said to be an insertion of a local operator. Okay? Just putting something in the path integral that is a function only of x of sigma. Okay? And points in its neighborhood. Arbitrary. Now, let's see. What was the prescription from going for computing correlation functions if you knew a state? The prescription was if you know the state on a disk of some radius r. Okay. You take the state at that radius r. Okay? Of x of theta. And then do the path integral dx of theta and dx of z of mod z etc. Okay? And put all your other operator insertions on 1 or 2 where they all have support outside this disk. This was our prescription for how to use a state to compute correlation functions of operators that are outside that. Now what we're going to do is take the limit r goes to 0. Okay? So now this integral over all the external x and all the external points is an integral over all points except 0. Okay? The integral over x at 0 is there because we're doing this integral. The contour is struck into a point. Okay? And we're weighting the path integral with some function that depends only on the fields at 0. Now, we're not exactly at 0 because we're taking a limit. So at 0 and its neighborhood. Once we do some examples, we'll see the scale. Okay? But that's what a local operator insertion is. So, whatever this reduces to, when you take this side, go down to arbitrarily small size, is an insertion of something that depends only on the value of x at 0 and its neighborhood. And that thing is an operator insertion. Clearly, this operator insertion has the property that if we now make this insertion and did the path integral to the unit disk, you will get back your state. Because we're just undoing the time evolution that allowed us to shift the state. Okay? So, we have now established a map between Pranav, I'm teaching a class at the moment. Can I call you in about an hour? Thanks. Bye. Okay. Great. So, yes.
So this operator is basically an outer product of the vacuum and the side.
It's what? It's the
Outer product of vacuum and the side.
what do you mean outer product?
Get
Outer product of vacuum and this. You're saying that it's zero size, something like this?
Yeah, something like that. But it's not the way.
Yeah, that it's this. Right. See, to talk about this, you're talking at a given time. Yeah, so it's something like this at t equals minus t.
Yeah.
Yeah.
So what I'm worried about is that this operator might not have a nice classical representation in terms of x's and p's, x's and pi's, whatever.
Okay. That it might not have a nice classical representation in terms of x.
Yeah.
Well, as long as every well-defined insertion within the path integral does, then you're guaranteed it would. Now, in ordinary quantum mechanics, any function of x just becomes a function of that operator. Any functions of x and its derivatives becomes functions of x and omega. Okay? So, unless something weird is happening, it will. Now, to completely convince you of this, I'm going to have to show you many examples. Okay? And we will see many examples as well.
Like, when you string to the radius pieces, like we are going from state to operators.
Yes.
Suppose there are some singularities, like some log singularities.
Yeah. So actually there will be power law singularities. But those will be what is needed. You see, why are there power law singularities? It's because a given state is a linear combination of states with given energies. In Lorentzian space, time evolution is evolution by a phase corresponding to these energies. In Euclidean space, time evolution is corresponding to a number with these energies. Okay? And the time evolution is just z to the power e, roughly speaking. So there will be singularities, but only power law singularities. Because every state can be expanded in a basis of states that have definite energy. Okay? Now these power law singularities will not hurt us, but will be what we need to define good operators. Hang on a little more to see some examples. This will become much clearer as we see examples. Okay? But what you are touching on is the fact that sometimes, in order to define an operator, you need to put some singularity so that the answer is not singular. We will see many examples as we go. Okay? Yeah.
As per Ronald's question, can't we just argue it by the way we constructed the operator by moving?
Sorry, what was it? You'll have to remind me of the question.
The question about this operator that you have constructed being a local function of position and momentum.
Yeah.
The way we have constructed and the way we have argued that when we go to r equals to epsilon, everything is defined only in terms of in that region, all the points inside that region.
Exactly.
That tells you by construction that this operator can be written locally.
Exactly. So basically it's some function of this, and then in Schrodinger representation, that function is just replaced by that operator. So as long as that function is not terribly behaved, it will work. I think Ronak is worrying about, there's some limit going on. And in that limit, that function may become crazy. Roughly is what it's related to Schrodinger. Okay? Such abstract arguments run the risk of being total nonsense in the absence of a few examples. Once you see a few examples, you will see how things work. But I agree with your general sentiment. This is also, yes, this one. Okay, I agree. Okay, other questions or comments? Okay? Now, this map between states and operators is, we argued it in an almost trivial way. But it's a beautiful and deep thing. Please.
Where is the locality of the operator components to this when the insertions are happening on cylinder? It's no, right?
That is not a local operator. Sorry, suppose you I think your question is going to be why do you have to take the R goes to 0 limit? Is that the question?
No, I'm asking on the cylinder, where is the locality of the operator components? It is a local insertion on the cylinder.
This operator, once you define it, is a local insertion into a path integrity.
Yes.
And once you understood as local insertion into a path integrity, it's a local insertion wherever you are. Cylinder, plane, genus 20 surface.
Okay.
If you understand what a local insertion does, you've understood the local insertion. Okay? So we've mapped this state on the cylinder to a local insertion into the path integrity. And a local insertion, once you understood what the local insertion is, it's just local insertion. It's an operator. An operator can be defined anywhere. It's a local thing, so you don't care what your manifold was. Was that the question?
Yes. So what exactly? Why can't we read this?
So you can. See, the claim was that there's a map between states on the cylinder and operators. I don't need to say operators in R2. Because operators are local things.
Yes.
So that's the claim of the map. States on the cylinder. Okay? We found it, of course, convenient to use R2 to generate this map. But once you got the map, it's a map to operators. Understood? You had a comment?
Yeah. But the point at the origin of R2 maps to this whole circle on the cylinder, right?
Yes.
So anything that looks local on this R2, I would say is non-local on that cylinder.
No, that's right. So if you take this thing and make it an insertion on the cylinder, that's not a local thing. But that's not what you do. Once you've got a function of x of z, you can go back to the cylinder and at any point on the cylinder, weighted by that function of x of w. Because that's an operator. An operator is how to deform a path integral by some local function. Once you've got that local function, you can deform any path integral you like with that local function. Okay? So what we're talking about is not taking this operator insertion and mapping it back to W. What we're talking about is defining an operator insertion. Once an operator insertion is defined, you can insert it into any path integral. Is this clear? Okay, excellent. Excellent question. Okay, so let's move on. I want to first show you, no, this is all taking a bit longer than I thought, but anyway, let's move on. I want to first show you a use of this thing. And the use of the state operator map is an incredibly simple derivation within conformal field theories of what is called the operator product expansion. Okay? So we will both derive as well as explain the operator product expansion in this incredibly simple way, even for people who have seen it before. By the way, if you look at Weinberg's book, quantum field theory, in the chapter on the operator product expansion, your head starts to swim. Okay, it seems incredibly complicated because he's trying to work in generality. In conformal field theory, it's very simple. I mean, very simple. Both the notion as well as proof. The notion is the same as everything. The proof is very simple. Alright. So, what is the claim of the operator product expansion, at least within a conformal field theory, where we can make a very precise claim? Okay, claim. Suppose you've got two operators inserted so near to each other that it is possible to surround both operators with a disk which excludes all other operators. Okay? Then the correlation function of these two operators is the same, involving these two operators and everything else, is the same as the correlation function of, so this is equal to for one effective operator inserted at the center of the disk. The important point about the statement is not that this is true for any particular correlation function. That's almost trivial. The important point about the statement is that this statement is true with the same operator for every correlation function. So irrespective of what else you have inserted outside, you can once and for all replace two insertions of the operator by a single insertion at the center of the disk. And that is true no matter what insertions you choose to make or not make outside the disk. alluded to when I talked about the chapter in Weinberg's book. This statement is, is believed to be true in quantitative theory in general. It's a bit hard to see exactly where. It's not so hard. But here is obvious. I'm going to prove it to you now in under a minute. Okay? What is the proof? You see, put these two insertions and do the integral over this disk. That gives you some integral that is a functional of the values of the fields at the boundary of the disk. But we've seen that a functional of the fields in the boundaries of the disk is a state. But any state can be replaced by the state operator map, by an operator insertion at the center of the disk. This is true no matter what you put outside. And so I've proved this. Is this clear?
But this operators has to be infinitely close to each other.
It has to satisfy only the following property: that it is possible to surround these two operators by a disk which contains no other insertion. That's all this is. Once this is needed, my proof goes. Once this is satisfied, my proof.
Are we not going back to this point that the map between the operators and states is going to be unique?
Why is it not unique?
Because you have a single operator which can give you a single state. Now you have two operator insertions which also give you a single state.
No, but you see, the map was between local operators and states. This thing is not a local operator. It's a product of two local operators. So this goes back to the point we started with at the beginning. That it was impossible, to have a unique map between matrices and columns. So in the space of all operators of the theory, there have to be redundancies. The unique map was between local operators and states. Now you start doing things that are not local operator insertions. You still get states, but these states then can be mapped to local operators. That's the point. Excellent. I want to emphasize that the map between local operators and states is entirely unique. One-to-one correspondence. How have we seen that? Because we've seen how to go from one to the other and the other to the one. We've seen how to go both ways, therefore it's unique. Okay? Excellent. So now, let me just say in a little formula what people usually use this operator product. Suppose you have O1 of Z1 and O2 of Z2. The way people write this operator product expansion is, for instance, that this is the same thing as O of sum over M, OM of Zn by including some functions of Z1 minus Z. Let's call this Z2. Where this OM runs over some standard basis of operators. How do we know, by the way, that there is a good standard basis of operators in terms of which any operator insertion can be written? How do we know that? We know that from the state operator. Because we know from the structure of the Hilbert space of states that there is a good standard basis of states in terms of which any operator can be written. For instance, we can choose this basis to be one in which the Hamiltonian is diagonal. Okay? And by the state operator map, then there is a good standard basis of operators in terms of which any. Okay? We will encounter this operator product expansion again and again and again as we go on in our study. Okay? So, it's important to understand the basic idea, the basic statement and the derivation. Any questions or comments?
You could write the OP between these two operators as long as there are, no matter how many there are, as long as there are no other insertions or...
As long as you can enclose them by a disk which contains no other operator insertions.
Simply analytic, no singularity.
As long as you can enclose them by a disk that contains no. That's it. Nothing else to say. Right? It's a very precise statement here. In ordinary quantitative theory, when they come near enough together, how near, all that. It's very precise.
In one-word creation and all those, they use the fact of hierarchy behavior of this operators.
Yes.
So how does it concept with this? Like, is it like that's why I was asking that whether it's like you have to take those.
Yeah, you want to know how the usual derivation using diagrammatics goes over to this.
No, that's a wrong.
I would have to think about it. Yeah. Yeah. In the case of the formal field, Jerry, you never think like that. Just so much cleaner way. Okay, excellent. Now,
So a new operator that you insert could have been at Z1, Z2, or any
could have been
other point.
anywhere as long as you as long as you could include both operators with a disk centered at that point. Okay? As long as there is a disk centered at that point, which encloses both operators and no others, then you can choose the insertion to be at that point. We will often choose, when we actually work with the operator product, the insertion point of the new operator be the position of one of the two operators. You might think we should choose the midpoint, but traditionally one chooses one of the two operators. So there we are assuming that there is a disk centered above this point and encloses the second operator with no others.
So the argument is Z2.
What?
So the argument
Is Z2, exactly. That's what I've done. That's just convention. Doesn't matter very much, but it's convention that everyone follows to be.
But yeah, if other insertions are such that if you take origin at one operator insertion and then some other operator might come in, then you are forced to.
Then you are forced to. But as you will see, again, what we use operator product extension for is for formal analysis. And for that analysis, we move our points to be where they are. They need to be. Okay. Yeah. But you're right. If you're in a practical situation wanted to do that, you may be forced to not choose this point. Because once you know it. Okay, excellent. Now, I want to the reason I talked about the operator product expansion and the state operator map now, the reason I brought this up at the beginning of this class, and it took me longer than I expected, but is to go back to our derivation of the word identity. Okay? In the derivation of the word identity, you remember we found that suppose there was an operator such that under the action of the symmetry, and the operator changed infinitesimally by some delta. Then we found that Jz times O, let's say 0, had a singularity that went like delta O divided by Z. That's what the Z1 do. That's what the Z1, the Z2, Z1 and Z2. Okay? Now, I want you to understand that this statement is simply, a statement of part of the operator product extension of J and O. Okay? Because what we're doing here is replacing the product of J of Z1 and O of Z2 by some operator located entirely at Z2. Now, in doing that, we will get operators of increasingly high dimension of the method. If you don't know what dimension is, we'll define it systematically in just a minute. Okay? But most of you have some intuitive appreciation of what that means. So we get operators of increasingly high dimension on the right hand side. Since the dimension of this times this is something fixed, we make up dimensions by putting in generically positive powers of Z1 minus Z2 to make up the dimensions. Okay, what I'm saying is that if you've got a term in the operator product expansion of J of Z1 times O of Z2 goes like OM of Z2. Let's look at the dimension of this guy. We're looking at holomorphic dimensions. Okay, pardon me for saying things before properly explaining them. I will explain them very soon. This is very roughly what it is. This is holomorphic dimension 1. Let's suppose this is holomorphic dimension delta. And this is holomorphic dimension delta n. Okay? Then we must have a term here which is Z2 minus Z1 to the power delta n minus delta minus 1 in order to match dimensions. Okay, because Z has dimension length, where we don't know dimensions of mass. In the infinite series, as we go along, in an infinite expansion in operators will get higher and higher dimension. Right? Because, think of the state operator. We've got a ground state, first exciting state, second exciting, but no limit, it goes off. Okay? So most states in this operator product expansion will have large positive powers of Z2 minus Z. But there will be a small finite number of operators that appear here, such that delta minus 1 is a negative. Okay? Those terms, as we will see as we continue to study, the wall identity is already showing us. Those terms here are particularly important in the operator product expansion. Those terms that appear with the singularity as Z1 goes to Z2 are particularly important. And what the wall identity was telling us is that the coefficient of the Z1 minus Z2 singularity in the operator product expansion between J and any operator is completely determined by symmetry. Okay? There is a term which is Z1 minus Z2, and its coefficient is completely wrong. Is this clear? Okay? So it's telling you about one of the possible singularities in the operator product expansion between J and J. Okay. Now that we've understood radial quantization, I'm going to tell you about another thing that is also sort of interesting. Okay? Suppose we had a symmetry generated by an entirely holomorphic current. Okay. So my current was that Jz is Z. What do I mean by that? By that I mean that insertions of Jz have del Z bar equals 0 except at possible locations of other operators. That's all I mean by that statement. Okay? I've got Jz, which is Jz Z, let's call it J1, and J2Z, which is J2Z. The two holomorphic operators, no anti-holomorphic paths. Now you remember that in our discussion of the wall identities and in our discussion earlier in this lecture, we described how an operator inserted at a constant time in W plane was this normal dot product of J with the contour over a constant time slice. So the charge corresponding to this operator is integral Jz dz. Okay, Q is integral Jz dz at a particular time, which in our quantum means at a particular radius. Okay, so this is Q1. Q2 similarly is integral Jz to dz at whichever radius you wish to start. Now, what I'm going to do is to ask, what can we say about the commutator between Q1 and Q2? Can we compute Q1, Q2 commutator? Now, let's go back and remind ourselves. In ordinary path integrals, let's say quantum mechanics, how do we compute commutators? You might think that this is commutators of charge operators at the same time. It doesn't matter because it doesn't. But we'll see in that soon. Yeah. So, but how do we compute an ordinary path integral? This sounds hard because you see a path integral automatically gives you an ordering of the operators. The ordering is time ordered. So you don't have it, if you put insertions into a path integral, you don't have in your hands how to order the operators. It's just given by time. But you can solve that by the following ordering. You just think of the commutator as the following insertion in a path integral. First, we have to remember that quantum mechanics is like Arabic, right? It's right from right to left. Okay? So, if you want, suppose I want Q1, Q2 at some time t, that is Q1 at t plus epsilon, Q2 at t. This insertion, in the limit that epsilon goes to 0, gives us the insertion Q1, Q2 at time t. This insertion into the path integral gives us the following operator insertion in Hilbert. On the other hand, suppose I wanted the other way around. Suppose I wanted Q2, Q1. Okay? That is the same thing as the following insertion into a path integral. Q1 at time t, Q2 at time t plus epsilon. This insertion of the path integral would translate in Hilbert space language to insertion of Q2, Q1 with that order. Because the path integral always orders things that are later to the left. Okay? So, it's a standard trick that if you want to compute commutators within a path integral, Q1, Q2 at time t, what you do is what we talked about. Q1 at time t plus epsilon, Q2 at time t minus Q2 t plus minus Q2 at t plus epsilon, Q1 at time t. Okay? If you want, please. If you want Q1 to the left, you have to put it at a slightly larger time. You want Q2 to the left, you put it at a slightly larger time. Take these times to 10 to t. That gives you the commutator. Now we're going to apply the standard trick to computing the correlation functions of Q1 and Q2 defined by these contour integrals. What is time in our case? It's radius. It's radial quantization. Okay? So what is time? It's radius. So suppose I want to compute Q1, Q2 and J2 taken here is equal to just because we put Q1 later than Q2. Let's further out is later. That's clear? What about the other contour? Suppose I wanted Q2, Q1. What do? I do the following. Now, by the way, we should be doing all of these at the same time and so on, but doesn't matter. No, because in our case at least, our Q's are holomorphic integrals, holomorphic contour integrals, with singularities only when the contours cross. So suppose we've got insertions here. As long as we don't cross any of the insertions, or this contour does not cross that contour. Any relative ordering of this, you can zigzag and do whatever you want. Because one contour stays entirely outside the other. That works. Okay? Excellent. So that's Q1, Q2, that's Q2. Now what I want to do is compute Q1, Q2 minus Q2. So what I'm going to do is the following. Let me choose the Q contour, the blue contour on both the diagrams to be, or maybe let me choose the red contour on both the diagrams to be over the same radius. Here the blue contour is a little bit above, and here the blue contour is a little bit below. Okay, now what's happening on the red? What we're doing there is integral dz changed to z. Let me do this integral, the red integral, last. I'll first do the integral over blue, and then do the integral over red. So, I'm going to do the integral over red later. The red, when I'm doing, the red point is at some point. Let's say this is the point. Now I want to do the integral over blue. So what do I have? I have to do this integral minus this integral. Okay, yellow is the other blue on the other side. But doing minus of contour integral The same as doing the integral with the reverse sign. So, we freeze this point here, where the z2 in, where z2 is, we freeze it, and then we have to do the blue integral on the following, disconnected contour. And this is on this one. But you see, now because we've frozen the z point, what the red integral is doing, contour of the red integral is irrelevant. We've got only this point. Everywhere else we can deform these contours. So these guys can go and meet each other and annihilate. And what are we left with? We're left with what is the answer to this? The answer to this is the residue of the singularity between Z1 and Z2 in J1 and J2. So suppose J1 of Z, J2 of 0. Z1, Z2 goes like, it has general operator product expansion. But suppose that the pole term is some O, whatever, O of Z1 minus Z2. Make that call it. Res Z2, Z1 minus Z2. This thing just picks up to a factor of 2 pi I. It just picks up res of Z2. Then what we're left to do is to take the res of Z2 and integrate it over the full rate constant. So the answer of Q1, Q2 is another charge. It's a contour integral. It's another generalized charge, some operator integrated of up to factors of 2 pi I, which we'll get straight when we're actually using this. Res Z2. Okay, dz. What we have seen here is that the operator product, the poles in the operator product expansion between two currents determine the algebra of the corresponding charges. Okay? So, there's this other beautiful, hop step you can play. Instead of talking about algebras of symmetry groups, you can talk about the operator product expansion of their corresponding currents. Okay? So the operator product expansion, particular terms in the operator product expansion of currents completely capture the algebra of symmetry groups in two-dimensional conformal field theories. And as you will see, by far the most convenient way to think, it's not in terms of the algebra, except for very special purposes, but in terms of the operator product expansion of the currents. You can easily go from one to the other once you know what you're doing. Is this clear? Is this clear, everyone? Okay, we take 15-20 minutes extra. Is that okay? Okay, excellent. So now we've completed our general discussion of Noether's theorem. We've talked about how we get this, the thing that we get in our discussion of Noether's theorem is a charge integral. And we talked about the singularities of this charge integral acting on this.
If there are double poles in the J1, J2 OP, then how can we?
They don't matter, because double the poles integrate to 0. It's a great thing. You can have a z to the m. If m is less than -1, you don't care. If m is greater than -1, you don't care. It's only m equals -1 that gives you non-zero. It's Cauchy's.
That is the CTOP.
Yes. We're going to talk about CTOP perhaps even in this class, depending on speed. Okay, excellent. So we've discussed the general structure of Noether's currents, Noether's theorem, operator product expansion, in interplay between symmetry algebras and operator product expansion. It's all very beautiful stuff. If this is the first time you're encountering it, you need to think about it. And you need to play around with examples, as we will. Okay? But now, motivated by your question, I'm going to move on to the discussion of a particular symmetry algebra that will be of great importance in the study of correspondence field theory, simply because it is the symmetry algebra of conformal invariance. Okay? And we will determine the currents corresponding to this symmetry algebra, try to understand their OPs, and move on. Okay? So, to start this discussion off, I'm going to now try to derive the Noether current. I'm going to now try to derive the Noether current for translations in space-time. I'm trying to consider Noether current for translations in space-time. The corresponding current, of course, has a name. It's called stress tensor. Okay. So you remember that. Okay. Now when we actually use it, we use various fancy factors of 2 pi I alpha prime and so on that Kulczynski puts in this general discussion, since they make no difference in particular. So you remember that suppose you have some x mu, and you make a translation. So x mu goes to x mu plus delta x. So let's say that x mu is equal to x mu prime plus delta x. Okay? What exactly does this symmetry transform? This I'm trying to. Okay. Let me call that epsilon. Okay. Let's say epsilon is a constant. So actually, first, yeah. Let's ask. Suppose epsilon is an arbitrary function. This translation is some sort of putative symmetry transformation of fields. What transformation? If all our fields are just scalars under diffeomorphism, the transformation is simply as the x field is delta x is equal to minus epsilon mu del mu. Why did I say this? This is an almost obvious statement, but I wanted to say this to emphasize something. Then you see, little x mu, I should call it sigma mu, right? Little sigma mu is just a coordinate parametrizing fields in the path integral. A symmetry operation is a change of variables of fields in the path integral. So to say sigma goes to sigma plus delta sigma and call that a symmetry operation in the path integral makes no sense. When we say sigma goes to sigma plus delta sigma, that's simply a code word for saying this. That's simply a code word for saying this. Okay? It's a code word for saying that x prime as a function of is the same function x but viewed as a function of x prime. X prime, sigma prime. Sigma prime is this. So it's x tilde is of sigma prime is equal to x of sigma prime minus epsilon. And then you take x. Just in terms of functions. Okay? So when we say this, what we mean is this for every field in the theory. If the fields carry vector or other more complicated transformation indices, we may mean slightly different things as well. For translations, there's no issue. You just translate everything. It's just plain simple translations. Okay? What we mean is just how every field in the problem is transformed, and for scalar fields, this is what we mean. Okay? So this is the symmetry transformation under which, okay, now, for general epsilon of mu, this is not a symmetry of a theorem. However, for epsilon of mu equals constant, this is a symmetry of a theory because our action is translation theory. Okay? So, the Noether current generated transformation. The transformation of translations in X, constant translations in X. That transformation there will be the stress tensor. Okay, so now let's remember our Noether procedure. Our Noether procedure said what we should do is to take our transformation parameters, make them arbitrary functions of X. So we go through this situation. And when we do that, we will find that delta S up to some factors which I'm not talking about. Okay? Was J mu, del mu of epsilon. Now this epsilon itself carried an index. Okay? So under the kind of thing that we want here, let's call it nu. And we've got epsilon, let's say mu. We'll call this T mu. So we know on general grounds that if we make such a translation that in general depends on X, the action will change. It must take this general form. And this T mu, whatever it is the charge count corresponding to mu translations. Okay? This is the current index. This is which translation index. And this object, whatever it is, we will call the stress tensor. It's just the Noether current for translations. Now, there is a second way of looking at this Noether current, which is often very useful. And that second way goes this way. So far, we've just been talking about a field theory in just plain flat space. But suppose we had a field theory coupled to a metric. Okay, imagine that we put in the action. In the action, we had the action coupled to an arbitrary metric. That metric may happen to be at the point of interest, eta mu. But we know the action coupled to it, neighboring metrics. Now, suppose we do this object here is just an infinitesimal diffeomorphism. So suppose we transform both the fields as well as the metric under this diffeomorphism, S will not change. Because that's a property of diffeomorphism, leaves the action unchanged. Okay? So, we've got an action, really, we're talking about path attack mechanism. Okay? Now, we need to actually, we're looking at one field theory where metric is not a dynamical degree field. So this is not what we should be doing, but we're just using this as an analytical trick. So in order to evaluate how the action changes under a transformation of fields under diffeomorphisms, we can as well evaluate how the action changes under transformation of the metric under diffeomorphism with a minus sign, because the sum of the two don't change the action. The action and the path integral, including the measure, if you assume everything is okay. So, but how does the metric change under a diffeomorphism? Like this. Well, all of you know that delta G mu is equal to del mu eta mu times plus del mu. It's a famous formula for the variation of a metric under an infinitesimal diffeomorphism. Okay? So, up to a minus sign that you have to think hard about to get right. Okay? You can equivalently define T mu as delta S is equal to integral delta, say the Lagrangian by delta G mu. I mean, the change in the action is this times this constant. Now, since this variation is symmetric in mu and nu, we can make a factor of 2 and keep just one of these terms. Let me keep this one to match with this.
Since it is around flat space, we can just
We can replace this by del nu, and you see that this is in this form. Once we make the identification, d mu nu is equal to plus minus. I need to think to get that straight. Probably plus 2 del.
These two definitions might differ with some
total errors. Exactly. Completely right. So, what Mangesh points out is that, you see, the action will be unchanged under diffuse opposites. But it could be that the way that works is that it changes by a total derivative. Okay? In which case, these two might differ by something that is relatively trivial, and you can show it by itself conserved. It's called an improvement term of the stress tensor. But the point is that you can always, you can always make one choice of that improvement term. You see, these improvement terms are things that are identically conserved. So, given a conserved term, you can always add something that's identically conserved to the conserved term, it will remain conserved. Okay? So, you can always make one choice of improvement terms such that we get this as our definition of the stress tensor. So, the stress tensor corresponding to translations, the notice corresponding to translations, has another very nice and interesting definition. It's identified with the variation of the Lagrangian. Okay, the variation of the Lagrangian, the derivative of the Lagrangian with respect to Jimmy. Okay. Now, 5-10 minutes more, basically. Okay. We're going to use the stress tensor heavily in what follows. Okay? And in particular, let's see. Okay. This formula for how the action changes under variation and arbitrary diffeomorphism will be very useful. Okay? So now let's in particular study diffeomorphism such that delta z is equal to epsilon z of z, and delta z bar is equal to epsilon bar z bar. Let's go epsilon z bar z. These functions are complex conjugates of each other for the excellent reason that z and z bar are complex conjugates. Okay? Suppose I had an analytic change in z and z bar. Okay? Now, what do I know about such coordinate transformations? We know that such coordinate transformations are symmetries of the theory. Okay? At least if we were looking at our X theory, we know that that's true. And this is what we're going to use as our, and we know that it's true for any conformity theory. Because these are precisely the kind of coordinate transformations that change the metric in a way that can be compensated by a Weyl transformation. Okay? This is the definition of conformity. That such coordinate transformations are symmetries of the theory. Now, how does the action change under such a coordinate transformation? Okay? According to this definition, the change of the action is T z z del z epsilon z plus T z bar del z bar epsilon z bar. If this has to be symmetric, this has to vanish. Okay, so lowering this is T z z bar into del z epsilon z plus del z bar epsilon z bar. Since epsilon z and epsilon z bar are arbitrarily analytic and complex conjugates of those analytic functions, the only way this can vanish is if T z z bar equals 0. Okay? So in a conformal field theory, it is both necessary and sufficient for T z z bar to vanish in order that arbitrary conformal transformations are a symmetry. Is this clear?
del z tz bar and del z bar tz bar vanish? Because we can take out the total derivatives.
Because we can take out the total derivatives. No, but you see, this was the local change in the action. But also this and this are not the same thing. This is a complex quantity of that. So suppose we go to a given point. This is a different number from that. So you want both of them to vanish.
Yeah.
So you're saying that what if the t and z bar is just constant? Let's see. No, but okay, let me think about that. See, our definition of this of a symmetry was that the change in the action was equal to something times del mu of epsilon. And we just want this change in the action to vanish. So this is not zero, it just doesn't vanish. I could choose this to be a delta function. I could choose this guy to be a delta function. So it just has to pointwise vanish. It's not sufficient that it vanishes after some integration by parts. It just locally has to vanish. I think. Well, let me think about this.
Because
your point is that these are not arbitrary variations because they're derivatives. So because of that, if that was just a total derivative and this epsilon was it wouldn't work. For instance, suppose t z bar was not 0. Then this thing wouldn't be invariant under scale transformations, even if it was just a constant. But of course, constant is just some factor I need. I think it wouldn't work. Let me get back to you next time with a good answer to your question. Okay, try to make a serious answer to your question. Your question was what if t z bar was just a constant?
Because the conservation of stress tensor from that definition came out because we took out the total derivative and transferred it on the TB.
Yeah. But there we were using the fact that epsilon of z was in our hands. You remember what we did there was to take some known epsilon and multiply it by an arbitrary function of x, which we could then take to vanish smoothly. For instance, here, one of the epsilons is just after scale transformations. Okay? Where delta z is z. Again, this is some given function. You don't have the freedom to make it vanish at infinity. It doesn't vanish at infinity. And it actually, if this was constant, just wouldn't work. You wouldn't get scale invariance. Because this thing just would not vanish under that transformation. Then you could make it formally look like it does by this integration by parts, but you would get an infinite contribution from the surface integral infinity. I think that, I'm pretty sure that it doesn't work. I don't think it works.
Just simple here. This will be the lead derivative type of thing. So it should leave the metric constants up to that factor. So if you see this delta GB, there's some kind of lead derivative. So that way can you think about this? Like delta z, ez, and delta z bar. There's some kind of symmetry there.
Yeah, I just think that, there's this quantity, which is some given number. This guy must just pointwise vanish. I think it's basically just that. That t z bar just must vanish. Okay, for instance, we can take an example, right? We could take the example that epsilon z was z. Epsilon z bar was z bar. So this is a constant. This is a complex conjugate. This thing must vanish. It just wouldn't. Yeah. Okay. Excellent. Okay. So, fine. So what we have seen is that t z z bar vanishing is both necessary as well as sufficient to ensure invariance under conformal transformations, because This one condition is shall not just invariance and the scaling transformation, special case that I talked about, but all of them are the same actually. Now what we want to do is to compute the Noether current. So now what we have is that Tz bar equals 0. This is of course a statement. Okay. This is of course a statement for insertions within path integrals, as always when we talk about operators. Okay. Now we've got this Tz bar equals 0. That's nice. Okay. But I want to now compute the currents that we get for all the various symmetry operations of our theorem. What are these various symmetry operations? Delta Z is equal to Z to the power n. And correspondingly, let's say an. Correspondingly, delta Z bar is equal to an bar Z bar to the power n. For all n, gives us a basis of these conformal transformations. N, by the way, will be positive as well as negative. Okay, it gives us a basis for conformal transformations. What I want to do is to compute the Noether currents for each of these conformal transformations, for each of these conformal transformations. Once again, what I do is to use this, the general formula for how the action varies under an arbitrary degree. What do I have to do? I have to take this an and make it an arbitrary function of z and z bar. This also make it an arbitrary function of z and z bar. And then just compute the change in the action. Okay. So, what do I get? I get that delta S is equal to integral. What was our general formula? It was T mu nu epsilon nu del mu. Okay. Now for epsilon nu del, let's do the analytic part. We'll do the anti-analytic part. Because delta Z is this part. So epsilon Z is this. So since this is, so that's T Z. And then here we could have had either Z or Z. But if we put a Z, we know that we get 0. So the only part that contributes is Z bar. We get dz bar of A of n times Z to the power n. Okay? But by the general prescription, this quantity, the coefficient of this quantity, is the current corresponding to the symmetry operation. Or more precisely, the coefficient of this quantity is the Z bar component of the current corresponding to the symmetry operation. Right? Because what was the rule? You've got some symmetry operation, you make the thing a function of opposition. Whatever multiplies the derivative of that function is the current.
Sorry, how is A a function of Z bar?
What? A is now promoted to an arbitrary function of Z.
Oh, right.
Right? Of course, the Z dependence of A doesn't matter because that's just some other conformal. But the Z bar does. Okay? So, JZ bar. So JZ, because this multiplies JZ bar up here, but I lower, that's JZ, is equal to the coefficient of this guy. So Z to the power n dz bar. Okay? And similarly, JZ bar will be equal to Z bar to the power n, and which is just dZz. Okay? dz bar. So we have concluded that the Noether currents for the various conformal transformations are extremely simple. They are obtained by taking tzz multiplied by z to the power n and tzz bar multiplied by z bar to the power n. Okay, Now there is one more operation, one more relation that we want to use. Remember that T mu nu was a conserved current. Okay? T mu nu was a conserved current. So this is the relation that del mu, let's say del mu, T mu nu is equal to 0. Let's view this in ZZ bar language. Okay? This is del Z Tz bar Z plus del Z bar Tz Z is equal to 0. One of the equations where the free index is Z. The second equation where the free index is Z bar is del Z Tz bar Z bar. Del Z Tz bar Z bar. Yeah, that's right. Plus del Z bar T Z Z bar is equal to 0. But we've already seen that TZZ bar is 0. So this equates to. So this tells us that in a conformal field theory, TZZ is an analytic function of Z, except possibly points of insertions are other operators. It's always what this means. Right? Whereas TZ bar Z bar is an anti-analytic function of Z. Now, once we understand this, can we, with our eyes, say that this gives us conserved terms? Of course it does. Because this is Z to the power n times an analytic function. Okay? And this is Z bar to the power n times an anti-analytic function. So we're in a situation that we discussed in the previous class, where we've got conserved currents because the analytic part of the current is an analytic function of Z, and the anti-analytic part of the current is an anti-analytic function of Z. So all of the analysis that we described, including the derivation of these, the transformation of word identities into statements of operator product expansions, applies perfectly to the situation. So perfectly to the discussion of the analysis of the analysis of conformal transformations. In particular, the commutation relations between the charges corresponding to each of these symmetry generations is completely captured by the operator product expansion of the corresponding currents. But the corresponding currents are deadly simple. Okay? They're just the stress tensor times functions of coordinates. So all of the symmetry algebra of conformal transformations, the full algebra of this group of conformal transformations, is captured by the operator product expansion of the stress tensor. And so the last thing we'll do in this lecture, and really stop, is to discuss what we can say about the structure of the operator product expansion of the stress tensor. Okay. Let me do this. We'll review next class. Let me quickly. Right. What I'm interested in, so now the notation TZZ will just denote by T and TZ bar Z bar by T. Almost everything that we do on the holomorphic sector will just be repeated with putting up our the anti-holomorphic sector. So most of our analysis will stick to just working out the holomorphic sector and leaving the others off. So the question I'm interested in is what is TZ T of W? What's the operator product expansion? Now, you see, I am interested not in every part of the operator expansion, product expansion, but only in singular terms. Because I'm interested in computing, for instance, commutators and so on of the corresponding symmetry algebra. Now, Mangesh might ask, why are you interested in all singular terms? You should be interested only in the pole. And you would be interested in the pole if you were interested only in computing the commutator of the charge builder of T and T. But we are interested in computing commutators of this kind. Higher singularities coupled with expansions of these z's will give rise to poles. But if you have no singularities, you will have get singularities. Okay? So much of what we are interested in, we're only going to worry about singular terms in this operator product. Expansion. Okay. Now, T is an operator with holomorphic dimension 2. And what do I mean by that? I should systematically introduce that. I will systematically explain what I mean by this next time. Right now, let's proceed with the intuitive understanding that we all have, that T behaves like 1 over z squared. Has the same weight as 1 over z squared. Why is that? It's because two integrals of T. One integral of T gives you an energy. So apart from that T is dimension 2 is obvious, right? Because the stress tensor integrated over space gives you an energy. Energy is dimension 1, integral is dimension -1. So the stress tensor must be dimension 2. Okay? So T is an operator of dimension 2. Because it's holomorphic, it behaves like holomorphic dimension 2. That is that you can't have any z bars all over the place. The dimension can only be made up with z's. So T is clearly an operator of dimension 2, and you want to saturate dimensions, you can't use z bars, you can only use that. That's all. I mean, I'll make it, more concrete and precise in the next class. But for now, let's just move on with this intuitive. This is an operator of dimension 2, this is an operator of dimension 2. Now, again, I'm going to quote a result, which the next class will justify, which is this following statement. That in a unitary conformal field theory, there are no operators of negative dimension. And the unique operator of dimension 0 is the identity operator. Yeah, we will show this in the next class. Given the statement, assuming we're dealing with a unitary conformal field theory.
Sorry, what is the statement?
In a unitary conformal field theory, there are no operators of negative dimension. And the unique operator of dimension 0 is the identity operator. Okay? Given this statement, what can we get on the right hand side of this OP? What is the maximum singularity we can get? The maximum singularity is 1 over z minus w the whole to the power 4. Because 2 plus 2 is 4. Dimensions must match up. You couldn't have anything negative here because there are no operators of negative dimension. If you have something negative here, you could get a high power here. That's not allowed. And if you have this power, this thing has to be proportional identity. So it has to be constant. Whatever the constant is, we call C of some number. Okay. Now, what about singularities of the form z minus 1 over z minus w the whole thing cube? You see, what about singularities of the form 1 over z minus w the whole thing cube? Okay? Some singularities are not allowed. Some singularities are not allowed from symmetry. You see, because suppose it was true that there was, suppose there was plus some operator, that's with some dimension 1 operator, of w over z minus w over. Okay? Then we will get that T of w, T of z, there's no difference between w and z. Just do the operator product expansion around point z. Okay? Is equal to T of C by Q, z minus w the whole thing to the power 4 plus O of z by z minus w the whole thing to w minus z. Thank you. Now let's look at the leading singularity. The leading singularity, let's say, expanded around z equals w. You just replace the z here by w. But the leading singularity here is minus of here, because this is minus this. The leading singularity, the w minus z cube singularity. Okay? Which is not allowed since these two are symmetric. This is the same thing. This was equivalence. It's the same operator product. Okay, the symmetry between Z and W, which forbids this kind of odd term. The only way you would have had such an odd term is if it was, we'll see where we can get odd terms. So this one is just forbidden. Okay, so that's not allowed. So, what can we have? The next term we can have is some operator of dimension 2 by Z minus W the whole square. Okay? We could have had some operator of dimension 2 by Z minus W the whole square. Please.
Can you use bigger dimension 0?
No, that was part of the theorem I quoted. That there is the only, in any unitary conformal theory, the only dimension 0 operator is the identity operator. It's never allowed. We'll see where that comes from. Okay, let's move on. So we could have something like this. Let's say that's over there. Then what will we get at order 1 over Z minus W? Now you might think that here we should get 0, but you have to be more careful. Because we have to do the symmetry, this fact that this is symmetric, we have to analyze it more carefully. Okay? So let's analyze this more carefully. Let's look at what we got from TZ, TW expanding around W. We got this. What do we get when we expand around Z? Okay, when we expand around Z, we get the same thing, right? We get T of Z, T of W is C by 2 by Z minus W square plus O2 of Z by Z minus W the whole square. Now, if we take this object and take the expanded around Z is equal to W, leading term is the same as this. That's good. But there is a subleading term. Okay? The subleading term involves the derivative of this O2. Okay? So this by itself is not symmetric at first subleading. Okay? This by itself is not symmetric at first subleading order. Okay? So we need a term at first subleading order in order to cancel the lack of symmetry. Okay? And this term, as you can see from here, is just simply D of O. That's the extra term that we need in order to cancel this over Z minus. Actually, if we write 2 over here, sorry, if we write 2 over here, we need D of O, because the thing that we need to cancel is D. But one will come with a plus, the other will come with a minus. So twice of that, okay, we'll have to cancel D. So I get rid of that by making this 2. So now the thing that we need to cancel is 2D. Do you understand? Okay, as I've said it badly, it's clear, right? Okay. And then class writing. So the operator product expansion of T with T on general grounds must take this form. Okay? The operator product expansion of T with T on general grounds must take this form. The same O2. Now what can we say about O2? O2 must be T. How do we see this? We see this, for instance, by once we know the operator product expansion between T and T, we know how T transforms under, for instance, a translation. Because that is entirely determined by the singularity of the OP of T with T. Do you see? What was the general rule? How any operator transforms under a symmetry operation. Okay? Is determined, okay, how any operator transforms under a symmetry transformation is determined by how that the operator product expansion between the generator of that symmetry and that operator. So now let us use T in both places. Let's see how T transforms under the symmetry generated by translations. What was the current for translations? Well, for general things it has this complicated Z to the N. But for translations, there's no Z to the power N. It's just T Z Z. So under a translation, how does T transform under a translation? It's just determined by the pole in the operator product expansion between T and T. But the pole in the operator product expansion between T and T is the derivative of O2. So we know that under any operator under translation transforms like its derivative. Okay? So this is all only consistent if this guy is T. That's right. So what we've done is to derive on very general grounds. Actually, we've assumed unitarity to get rid of that assumption using more clever arguments, but let's postpone that. At least assuming unitarity. We've derived on very general grounds the structure of the operator product expansion of two stresses. All singular parts. That is determined by one number that we don't know. Everything else is completely fixed. This del T has to come with coefficient 1. That's why we put this 2. Okay? I've gone through this fast. Okay? I'm going to request everyone to go through this little derivation we went through. For the next class, if you have any questions, we can start the next class with answering questions about it.
O2 can be the stress tensor plus the constant.
Constant, it has to be an operator of dimension 2. Constant's identity of dimension 6. So that's what.
This is just in 2-dimensional that identity cannot appear because in 4-dimensional if you take, say, is not 4 or something like
Well, sorry, say
2-dimensional, like the question that Manish was also asking, that TTO.
Identity can appear. It appears with the coefficient z minus w to the 4.
TTO type of operator.
If it appears with dimension z minus w squared by its scale invariance. Dimensions don't matter. Okay, it can, it doesn't. But with the right coefficient. Okay? This operator product expansion that we very quickly obtained completely determines the full symmetry structure of the conformal algebra as we will understand next class. Okay? So we're within sight of the end of this discussion of our first discussion of conformity theory. I have to estimate 2 more classes. Next class, the next one, and then we'll get back to our serious quantization.